Thank you very much for inviting me to present this talk at the HSDIP workshop. Before we get started, I would like to acknowledge and thank my past and present collaborators. A subset of them are shown here. Now, there are many applications that are examples of use of AI planning. Here are 4 such applications that I was involved with at IBM. Left top, this is the healthcare setting where the objective is to help users, nurses, physicians in early detection of health complications in the ICU setting. Top right, this is the energy domain example where the objective is to project the price and supply of oil in 10 or 15 years in the future. Down left, this is the risk management setting where the objective is to assist financial organizations in identifying and managing emerging risks. Down right is the automated machine learning setting where the objective is to automatically generate machine learning pipelines. Now, there are many common things between these applications. First is the existence of domain knowledge. There are domain experts who can provide the necessary domain knowledge, but obtaining this knowledge is also, of course, challenging to elicitate. For example, the type of knowledge for the healthcare setting can be provided by doctors or their books written on the subject. Similarly, for the scenario planning, there could be lots of articles regarding the cause and effect of different forces, and that can be explored. Second, people want more than one plan, either for explanation purposes or in the case of plan failure, or in general, wanting to have a better sense of what is possible. In some settings, they would want to have a diverse set of plans. In some other settings, they would like top high quality plans, and in some, diverse but bounded quality plans. And finally, humans are involved beyond just providing the domain knowledge. We have humans that interact with the tool. They need to validate, like what they see. They need the solution visualized and explainable to them. They also would sometimes like or dislike some solutions more than the others. And there should be a way of letting them indicate that in the tool. And of course, there are challenges as well. So modeling is and continues to be one of the reasons that would prohibit the use of AI planning. That is how to drive the planning problem in order to use the planning tools. And theory, how to compute a solution to the problem, what planning tools to use, etc. In some cases, you can use the planners that are available, and in some other cases, you end up creating a new planning theory and tools that were motivated by this particular problem or application, but can be used in any other application setting. And I'll give examples of those later in this talk. Now, to motivate this talk further, I will briefly drill down on one of the applications, that is the down left project on scenario planning. So what is scenario planning? Now, scenario planning is a commonly used enterprise risk management technique facilitating decision makers in formulating long-term plans by considering multiple alternative futures. Now, it is typically a manual, highly labor-intensive process involving dozens of experts and hundreds to thousands of person-hours. As a result, only a few scenarios can be constructed by humans. Also, bias can be introduced. So, for example, high-impact, low-likelihood events could be overlooked. So we developed a tool called SPA, which is a mature research asset at IBM that's available as an open service for non-commercial use. So with SPA, we see reduction in time for building scenarios from months to hours. We also see exploration of orders of magnitudes more scenarios than humanly possible. In fact, one of SPA's clients says, and I quote, SPA is 30 times faster in time to generate a dynamic risk model and the first scenario, and 3,000 times faster in time to generate the second scenario and each subsequent scenario. Now, this is comparison to human expert. So in the solution, we use NLP to automatically construct the models needed for planning. So this is the domain knowledge that's needed for AI planning, and it's learned automatically. Now we use AI planning to explore the space of possible scenarios that allows us to automatically generate lots of scenarios. Then we choose the relevant scenario to present to the user. So for SPA, but also for many other applications or aspects of modeling, theory, and tooling that needs to be addressed. Now, a common framework that we adopted for the use of AI planning is as follows. As I mentioned before, we have domain knowledge, and the first step is to create a planning model. Now, that can be elicited or learned. Hence, we need to somehow address the modeling challenge, which is any gap between identifying that you have a planning problem at hand, that you can use a planner to compute a solution, to specifying a planning problem in a language such as PDDL in order to use a planner to compute a solution to the original problem. Then we need to run the appropriate planner to solve it. So find plans, sometimes lots of plans. Sometimes we need to create planners that are suitable for our task and are motivated by the problem we face. In fact, we have worked on a number of different planners such as top K planning, top quality planning, or diverse planning. All of these are motivated by the applications we face and yet are not domain dependent. That is, we make these planners available and the tools can be used by others. Then we need to do post-processing to translate the solution into a solution for the problem of interest and inspect the solution. This can be done by the users of the applications, which can be different from the domain expert. And oftentimes, you may need to adjust the model through feedback and start again. Now, one of the things you get for free with AI planning is that the plans are very much accessible and understandable by humans with perhaps just a good UI interface. So once the users view the plans, they can give feedback to the system and the models can be adjusted accordingly. Now, having this framework in mind, let's talk about the Scenario Planning Advisor SPA in detail. So first, how do you know it's a planning problem? So we characterize the scenario planning problem for enterprise risk through its corresponding plan recognition problem. Then we use plan recognition as planning technique, which allows us to use AI planning to generate scenarios. Now, in terms of modeling, we have to transform the available domain knowledge into an AI planning task. More recently, we automate this process and we automatically extract the causal models that can form the basis of the AI planning task. Then we use top K planning to generate a set of top K quality plans, which would then get clustered into 3 to 5 scenarios to show to the user. We could also use diverse planning or top quality planning to generate multiple plans as well. The users are able to provide their feedback and we modify the model if needed based on their feedback. So naturally, here's the agenda for the talk. I will talk about modeling, then theory, and then on tooling. For each one, I will talk about my experience and provide some hints or directions in terms of future opportunities. So first, modeling. As I said before, I consider any gap between identifying that you have a planning problem at hand, that you can use a planner to compute a solution, to specifying a planning problem in a language such as PDDL in order to use a planner to compute a solution to the original problem to be a modeling challenge. Now, this requires obtaining the knowledge, representing the knowledge, extracting it, and possibly learning it in PDDL, as well as validating it and enhancing it. So some modeling challenges are, we often need to transform the original problem to a problem with known or easier to compute solutions. So in order to solve the original problem, we have to do a transformation to another problem. For example, we cast the original problem as a plan recognition problem as we did with SPA, and then we can use AI planning to address it. Second, access to domain experts familiar with input to planners. For example, PDDL is very rare. And third, any form of knowledge is practically guaranteed to be incomplete and often inconsistent. Even human validation can be ambiguous. And finally, current state-of-the-art learning approaches may not scale and may have assumptions that may not hold for the practical setting. Furthermore, the learned knowledge may not be consumable by humans. Next, I would like to drill down more on the first challenge on establishing a relationship to AI planning. Sometimes it's trivial to write down a planning problem, but sometimes it's not. And you need to find a relationship to an existing problem with established connection to AI planning problem. I call this a planning problem in disguise. So you need to define the application problem, making a correspondence to AI planning. Define the computational problem, then reduce it to a planning problem or to a problem in which an established relationship to AI planning exists. This allows us to use AI planning tools to compute the solution. So, for example, in the case of scenario planning problem or SPA, we need to define the scenario planning problem, make a correspondence between the scenario planning problem and the plan recognition problem. That is, we link the relationship between the different forces such as technology, currency, social order, corruption, natural disaster to AI planning task. The drivers that user selects in order to perform their what-if analysis or the observations, and the implications, the drivers that have a special importance to the users or the possible set of goals. Then we leverage the existing relationship between plan recognition and AI planning to compute the solution to the original problem. Note that we sometimes have to extend the established relationships in a number of different directions. So for plan recognition as planning, we had to extend it to consider observations that are over fluence or properties of states and that they can be unreliable. So not all observations are explainable. Now I want to point out that there are several established relationships to AI planning that's often explored. Now find excuses, diagnosis as planning, explanation generation, as well as plan recognition as planning. They in turn help with hypothesis generation and exploration, future state projection, multi-agent plan recognition, as well as scenario planning. Now, in addition, I want to mention some other commonly used compilation techniques that come to rescue when it comes to the modeling challenge. So we have compiling away soft goals, which will let you use any classical planner to address the simple preferences or soft goals. And we have the translation from HTM problem into a classical planning problem, which will let you use classical planners or heuristic search in particular to find solutions for an HTM planning problem. Now, an example application where we have used the translation from HTM planning to classical planning, as well as the compiling away soft goals, is the automation of machine learning pipeline generation. Now, the problem is that we have a large space of possible pipelines, and humans can explore only a tiny portion of it. And humans are biased toward the pipelines that they're already familiar with. Now, the benefit of our solution is that we can generate pipelines of high accuracy automatically, and we reduce the need for human data scientists. Our solution uses planning tools for exploring the space of possible pipelines, defined with the use of regular grammars. And we translate the regular grammars to HTM planning problem, then to classical planning problem. We enrich the planning model with user-defined constraints, and then we use AI planners to solve the planning model and translate plans to pipelines. Now, to give a full picture of all the different translations and use of AI planning, showing here the overview of our solution to the automation of pipeline generation. Now, given a data science grammar, we transform it into an HTM planning model, then to classical planning model, and then we integrate user-defined constraints, turning the classical planning model to classical planning with soft goals, compile these soft goals away, obtaining again a classical planning model. We then use top quality and diverse planning to generate multiple plans. Then we post-process each result into a machine learning pipeline. These pipelines are then trained on specific data sets, and their accuracy feedback is used to adopt the planning model. Now, in order to focus the exploration of valid pipelines, we allow for specifying preferred non-terminal and terminal symbols. The non-terminal symbols correspond to the rules of the grammar, allowing to specify preferences, for instance, using a particular family of algorithms. Choosing a terminal symbols allows for preferring a specific algorithm or even a specific value for a hyperparameter. The preferences are then translated to soft goals, which are added to the classical planning problem instance. Then the soft goals are compiled away using the transformation proposed by Heider and Geffner, giving us again a classical planning problem instance. Now, in summary, modeling is an important aspect of use and adaptation of AI planning. Investing in transformational compilation techniques pays off. Learning a consumable planning model or even enhancing a planning model automatically is critical. And more investment is needed in supporting additional features of PDDL, such as conditional effects with costs, numeric planning, temporal planning, or axioms. Next, I will briefly talk about the theory. Now, there are lots of different computational problems for classical planning. We have cost optimal planning, which is about finding a plan that optimizes summed operator costs. We have satisficing planning. We want to find a plan. Cheaper plans are better. We have agile planning. We want to find a plan. Quicker is better. We have top K planning. We want to find K plans such that no cheaper plans exist. We have top quality planning. We want to find all plans up to a certain cost. And finally, we have diverse planning. There are a variety of different problems aiming at obtaining a diverse set of plans. Note that some of these computational problems were originally introduced and motivated by the applications, for example, top K planning for SPA, but now others are working on planners for those computational problems, and the planners we have developed can be used in other application domains as well. Next, I will briefly go over a more recent work we've done. In particular, we'll talk about a definition of top K planning, top quality planning. Then I'll go over the diverse planning taxonomy of our solution. And then I'll talk about two of the diverse planning problems, in particular SAT-K, or satisficing diverse planning, and BDK, which is diversity bounded diverse planning, and showed some experimental results. Now, top K planning aims at finding a set of plans of size K such that if a plan is in the set, then all plans with cost strictly smaller are also in the set. Top quality planning requires to find all plans of cost smaller or equal to a bound Q. Cushion top quality planning relaxed that requirement, allowing defining equivalence relation over plans and requiring the union of equivalent classes to be the solution to the top quality planning problem. An example of such equivalence relation is ignoring the order among actions in a plan which defines a so-called unordered top-quality planning problem. Our idea is based on multi-set forbid reformulation. It's adopted to forbid exactly the set of multisets and subset thereof. It captures plans that correspond to superset of previously found plans. Diverse planning, in addition to the quality, considers also the diversity of a set of plans. In 2020, we introduced the taxonomy of computational problems in diverse planning and mapped existing planners to these problems. Now, the hierarchy between the presented computational problems is shown here. Similarly to the separation in classical planning, we distinguish between optimal, bounded, and satisficing. The edges represent solution set inclusion, whether a solution for one problem is necessarily a solution for another, assuming a solution exists. For example, a Pareto optimal solution or optimal diverse planning is a solution to either optimal diversity diverse planning or optimal quality diverse planning, but not necessarily to either optimal quality bounded diversity or optimal diversity bounded quality, since the latter two optimizes over the solutions that are of bounded quality and diversity respectively. Top K planners can be thought of as a planner for optimal quality diverse planning. An LPG can be thought of as a planner for both satisficing diverse planning as well as diversity bounded diverse planning. Note that we have developed solutions to some of these computational problems, and for some, no planners exist. Now, previous work modifies the existing planners potentially through its heuristic to come up with plans that differ from previously found plans. Now, in contrast to modifying the existing planners, we do so by iteratively modifying the planning task to forbid plan sets. So our solution is based on our previous work, which we used to compute a set of top K plans, and it's based on planned forbid reformulation. We can now exploit any classical planners, and there's no need to modify existing ones. So we forbid all possible reordering of the same plan. So for example, if you have A, B, A, and then you have B, A, B in your set, then we also forbid not found plan A, B, A, B, but not A, A, B, or A, B, B. So based on the idea of reformulation, we propose the solution to two of the computational problems, in particular satisficing diverse planning and diversity-bounded diverse planning. So for the satisficing diverse planning, I have given a diversity metric D. We choose a subset of plans P of size K. Any subset of size K is a solution, aiming at a larger diversity score. Simple greedy algorithm iteratively constructs a set by adding the next best candidate. It's NP hard to optimize, and the straightforward mixed integer programming encoding does not provide encouraging results. Now for the diversity bounded diverse planning, we have given a set of plans, a diversity metric D and a bound B. We want to choose a subset P of size K such that the diversity score is bounded. All valid solutions are equal, and there's no simple greedy algorithm. We have a mixed integer programming encoding for pairwise diversity metrics. This is the evaluation of satisficing diverse planning. Our planner forbid iterative FIs compared to existing satisficing diverse planners on state, DS, stability, DA, uniqueness, DU, as well as uniform linear combination over all subsets of these metrics. We also varied the size of K, the number of required plans. For coverage, each technique gets a score between 0 and 1 for each task and each metric. If not enough unique plans were found by some planner on a task, the planner gets a score of 0 for that task. For our approach, Fi, we show the coverage number, and then we show the percentage of coverage compared to our approach for other existing approaches. In total, we have 1,276 tasks in 40 domains. Now, for solving the original and reformulated classical planning task, use the existing state-of-the-art planner Mervin. Note that while we report only on using Mervin, we have experimented with other planners and can potentially use any other classical planner. Now, in terms of the results, we can see that our approach does well, and the next best planner is LPG. Now, here's the result for a larger size K. Note that while for smaller K values, there are several techniques that are somewhat comparable in their performance to ours, larger K values seem to be very challenging for most tested techniques. Now, here's our result for diversity-bounded diverse planning, and we're comparing our approach to LPGD. Now, DA, as I said, is an average over pairwise stability similarity. DMA is a minimum over pairwise stability, and the measure that's used in LPG is the metric where stability is computed over multi-set, and that's called DMMA, and that is the metric we used in our experiments. Now here we showed overall summed scores over all instances, as well as the number of domains where each approach exhibits superior performance. So best results are bolded. DOM shows the number of domains with superior performance for BFI, which is our approach, bounded 4-bit iterative, over LPGD. Our approach chooses K plans out of the found plans above the given threshold. Thus, our approach has a clear disadvantage where there is little or no choice, as is in the case of the largest K values in our experiments. For smaller K values, such as K that's 5 or 10, there is a clear advantage to our approach for all tested bounds. Now, in summary for the theory section, so classical planners often come to the rescue, and we've seen that over and over again. And in diverse planning, there are some planners that we have developed, but there are some computational problems with no planners available. So you can potentially develop planners for the new formalized computational problems. You can also mix and match. So you can develop classical planners that support conditional effects or axioms that return multiple solutions, or have temporal numeric planners that return multiple solutions, HTM planners that return multiple solutions, or conditional effects and axioms in HTM planning. Now, in the last part of this talk, I want to very briefly talk about tooling. Now, tooling could mean two different things. One is the end-to-end solution for a practical application that uses AI planning. It could also be the planning tools, and we sometimes use tools to mention planners. Now, I will talk about both of them in some sense, and I'll talk first on the end-to-end solution for our applications. So we have to not forget that we're making a tool for human consumptions. So you got the theory, you know how to address the modeling challenge. Now you have to put everything together to come up with an end-to-end system. Some part of it has to do with the user. So you have the interaction with the user, how to obtain the model, sometimes select and obtain the observations, and also getting users' feedback. So you need to transform the data into a set of possible observations. So analyze large amount of raw data and select with the help of an analyst a sequence of observations to fit the system in some cases. And it's possible that the data that you have is noisy, and it's not always accurate. So for example, in the case of a healthcare setting, the data entered by clinicians is not always accurate. And transforming waveform sensor data to observations can introduce noise. And you also have the translation of the domain knowledge into an AI planning problem that needs to be automated, as well as post-processing of the plans into the solutions of the original problem. You also need to visualize the results and show them to the users. Now, in order to show the different aspects of developing an end-to-end tool, here's an architecture of SPA. The users provide their initial collection of documents, and they're able to evaluate and modify the automated constructed models. That's done through a questionnaire. SPA automatically constructs the model, and the planning model is then constructed and sent to the AI planner. The results are post-processed, and the relevant scenarios are presented to the user. The users provide their feedback on the scenarios, which in turn is used to adopt the model. There's also an awareness component that helps the user with the selection of interesting or relevant key drivers such as high inflation, increasing trade deficit, or increasing taxes. That is, the user is able to explore the recent news in order to give them insights into which drivers they can select for the generation of the scenarios. Now, exploring the generated scenarios will help users carry on risk conversations for their business, and users are able to do what-if analysis by selecting different sets of risk drivers. Now, here's an example of a scenario. SPA presents both textual as well as graphical view of a scenario. Now, for each set of scenarios, we see two categories, probable and possible. The drivers that show up in these categories show up not because of some probabilistic projection, but based on how many of these plans contain these drivers. That is, we generate lots of plans, we cluster them based on set similarities of last states. We then measure for each driver how often it appears in the cluster. So this is percentage of plans in the cluster that this driver appears in. We also have some thresholds that's adjustable by the user. Now, here's a graphical view of the same scenario. Now, with respect to color coding, we have green, which is the risk driver we selected, or this is the observations. We have yellow, which is the business implications or the set of possible goals. These are drivers that have a special importance to the business, and they're generally expected to be final nodes in the path. And we have blue, which are called leading indicators. They are drivers that generally appear early in one scenario, and they're discriminatory. They tend to lead to this scenario and not others. Observing these leading indicators could alert users as to which scenario is likely to occur. Now, to interpret this scenario graph, look at any node. The arcs from that node tell what that node might lead to, where it to occur. So, for example, high inflation could lead to currency depreciation against US dollar. Here I'm also showing two paths, which are basically the plans that found by the top K planner, one in red and one in green. Now, if you're interested to know more about the SPA, either send me a message or you can look at the full demo at that link. Now, there are many useful planning tools, some of which we've built and some of which we continue to use as a result of working on many of the applications that we work on at IBM. These include classical planners, top quality and diverse planners, numeric planners, as well as many problem transformations that will take you from one formalism to another. And more recently, we have made a number of domains and problems available. In particular, we have made available a domain that's inspired by the scenario planning problem. All of our tools can be found via that QR code. Now, in terms of tools and beyond, so you know that there are lots of planning tools that already exist, and there's a lot more in the pipeline. So there is PDDL editor, it's simple, plan utils, and so on. And we also have a number of end-to-end tools that I mentioned here. I'm putting the URL for the tutorial that I'm organizing together with Michael Katz and Octavian Udra. And you can go there to see all the tools that we mentioned in the tutorial. But we need to do more. We need to make the tools more accessible. The tools need to be easy to use and install. And in some cases, it's much easier to provide a Docker image than to give the source code that people need to run themselves. And it's worthwhile investing some resources on maintaining and updating some older tools that people still love to use. And furthermore, it's also important to advertise the work. Now there are a number of different ways these days people advertise their work. I'm just putting some examples here. You can write a blog post, put it on LinkedIn, your accepted papers, or present a tutorial. But I'm sure there are many other ways that you can advertise your developed tools so others can benefit from it and use it and give feedback as well. That's it. Thank you very much for your attention, and now take your questions. Thanks.